In this lecture, we introduced the Rayleigh Ritz method for finding an approximate solution to a second-order boundary value problem. For the boundary value problem on the finite interval from x equals a to x equals b, we take a function p of x which is at least as big as some positive value delta, a non-negative function q of x, and a third function f of x. We require that p prime, q, and f are all continuous on the interval. The boundary value problem is given by the equation minus d by dx of the product of p of x and dy by dx plus q of x times y equals f of x with the boundary conditions that y of a and y of b are both 0. The Rayleigh Ritz method relies on the following fact. Y equals y of x is the unique solution to the boundary value problem if and only if y satisfies the boundary conditions and is the unique function that minimizes the functional I of u, which is given by the integral from x equals a to x equals b of the quantity p of x times the square of u prime of x plus q of x times the square of u of x minus 2 times f of x times u of x. For a proof of this fact, we refer the viewer to a set of PDF lectures whose link we are including in the description of this lecture. In order to apply the Rayleigh Ritz method, we require a basis of functions or a set of linearly independent functions that we call phi sub 1, phi sub 2, etc., 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 all the way to phi sub n, with n being a positive integer. The phi sub j's must also satisfy the boundary conditions. The basis functions for this lecture will be what are often called tent functions. We call the approximate solution phi of x. Phi of x is equal to the sum from j equals 1 to n of c sub j times phi sub j of x. The c sub j's are unknowns, and we solve for these using the fact that the solution to the boundary value problem minimizes the functional. We find the c sub j's, we have our approximate solution. We find the c sub j's by assuming that phi of x minimizes the functional, and so we replace u by phi. Or we replace u by the sum of c sub j times phi sub j to get this form for I of phi of x. If phi minimizes the functional, then the partial derivative of the functional I with respect to c sub I should be 0 for each I from 1 to n. Differentiating the first integral with respect to c sub I, we get 2 coming down times p of x times the summation of c sub j times phi sub j prime. The chain rule dictates that we also need to differentiate this sum with respect to c sub I, and the only term involved is the term c sub I times phi sub I prime, whose derivative with respect to c sub I is phi sub I prime. Similarly, differentiating the second integral with respect to c sub I, we get this term. The third integral term gives us minus 2 times the integral of f times the derivative with respect to c sub I of c sub I times phi sub I, leaving us with minus 2 times f of x times phi sub I of x, with all the other terms in the summation vanishing upon differentiation with respect to c sub I, since they do not depend on c sub I. We cancel out 2 and factor c sub j from these two summations and move the integral of f times phi sub I to the other side to get this equation. We call this integral lowercase r sub ij. And we define uppercase R to be the matrix with entries lowercase r sub ij. We call this integral lowercase s sub I. We define uppercase S as the vector of the lowercase s sub i's. We define uppercase C as the vector of the lowercase c sub j's. Then the matrix system for solving for the c sub j's is given by the matrix R times the vector C equals the vector S. Using tent functions for our basis functions, we first partition the interval from a to b using the partition points or nodes x sub 0, which is equal to a, which is less than x sub 1, which is less than x sub 2, etc., 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 which is less than x sub n, which is less than x sub n plus 1, which is equal to b. Observe that we are using n plus 2 nodes, and therefore n plus 1 subintervals. Let h sub I minus 1 be the length of the ith subinterval so that h sub I minus 1 equals x sub I minus x sub I minus 1 for I equals 1 to n plus 1. We define the ith basis function phi sub I as a piecewise linear function. Phi sub I of x equals 0 when x is between a and x sub I minus 1 inclusive. Phi sub I of x equals x minus x sub I minus 1 over h sub I minus 1 if x is greater than x sub I minus 1 and less than or equal to x sub I, so that we have the line segment connecting the point at x equals x sub I minus 1 on the x-axis to the point at x equals x sub I on the line y equals 1. Phi sub I of x is equal to x sub I plus 1 minus x over h sub I if this time x is greater than x sub I and is less than or equal to x sub I plus 1. This piece forms a junction with the preceding piece at x equals x sub I on the line y equals 1 and connects to the point at x equals x sub I plus 1 on the x-axis. And phi sub I of x is 0 when x is greater than x sub I plus 1 and is less than or equal to b, so that we have another horizontal piece. The other phi sub i's have similar formulations and graphs. Phi sub I prime of x is then given by these formulas on the corresponding subintervals, so that the graph of phi sub I prime would look like a collection of step functions. Note that phi sub I prime is undefined only at the nodes or partition points, which is also why no nodes are included in the definition of phi sub I prime, unlike that for phi sub I. To determine the entries of the matrix R for this basis, we examine each integral in the formula for R sub ij, which we should point out happens to be equal to R sub ji. Note that the only time phi sub I times phi sub j is non-zero is when j equals I minus 1, j equals I, or when j equals I plus 1, because it is only when one of these is true that phi sub I and phi sub j are both non-zero over some interval of positive length. The same thing applies to the product of phi sub I prime and phi sub j prime. Phi sub I prime and phi sub j prime are discontinuous only at the nodes, and the nodes are isolated from one another so that the integral of phi sub I prime times phi sub j prime is still finite, granted that the integral is improper. Therefore, this integral will be 0 when j is less than I minus 1, or when j is greater than I plus 1, so that we count this integral only when j equals I minus 1, I, or I plus 1. First, set j equal to I. Then there are two intervals of integration to consider. The first interval is from x sub I minus 1 to x sub I, where phi sub I prime is 1 over h sub I minus 1, so that we get this integral for the left part of the first integral. For the other part, phi sub I prime is minus 1 over h sub I, and we get the rest of the integral of p times phi sub I prime squared. We determine the integral of q times phi sub I squared in the same way, using the formulations of phi sub I on the respective subintervals. We leave it as an exercise for the viewer to verify that by using the non-zero parts of phi sub I, these are the integrals one should get for the integral of q times phi sub I squared. Now we set j equal to I minus 1, and find the integrals for the entries R sub I minus 1. On the interval from x sub I minus 1 to x sub I, phi sub I prime is 1 over h sub I minus 1, while phi sub I minus 1 has negative the slope of phi sub I, so that this is what we get for the left part of the integral of p times phi sub I prime times phi sub I minus 1 prime. On the same interval, phi sub I of x is x minus x sub I minus 1 over h sub I minus 1. While phi sub I minus 1 of x is x sub I minus x over h sub I minus 1. So that the integral of q times phi sub I minus 1 on the same interval is equal to this quantity. The value of these two integrals between x sub I and x sub I plus 1 is 0, since both phi sub I minus 1 and phi sub I minus 1 prime are 0 on this subinterval. We now set j, equal to I plus 1. The integral of p times phi sub I prime times phi sub I plus 1 prime and the integral of q times phi sub I times phi sub I plus 1 on the interval from x sub I minus 1 to x sub I are both 0 since phi sub I plus 1 and phi sub I plus 1 prime are 0 on this subinterval. On the interval this time from x sub I to x sub I plus 1, phi sub I prime is minus 1 over h sub I, while phi sub I plus 1 has the slope with the opposite sign, so that p times phi sub I prime times phi sub I plus 1 prime is minus p over h sub I squared. On this same subinterval, phi sub I is x sub I plus 1 minus x divided by h sub I, while phi sub I plus 1 is x minus x sub I divided by h sub I, so that this is what we get for the integral of q times phi sub I plus 1 times phi sub I. Applying the same strategy to find the s sub i's, we should get this sum of integrals for s sub I. We leave this as an exercise for the viewer. Since each r sub ij is 0 if j is not equal to any of I minus 1, I, and I plus 1, the coefficient matrix R is tridiagonal. And since r sub ij equals r sub ji, the matrix R is also symmetric. We solve for the c sub j's using this matrix equation, and we obtain an approximate solution for the boundary value problem.